It's absolutely fantastic to be here, and I really mean it. I've done quite a lot of things in my life, but one thing that I really missed was to come and visit you here in Missouri. And I've heard about the fantastic work you've been doing here for such a long time, so I was very ashamed not to be able to come here before, and I'm very, very happy to be here finally. Better late than never. So great to see so many nice familiar faces, and I'm looking forward to meeting many of you that I haven't met before. And I'm here just on a very short visit. I was at the COP15 meeting in Montreal, the Conference of the Parties on Biodiversity, for about 5 days. Trying to support the governments of the UK, Sweden, the EU in the negotiations. Was very interesting to see how things were going or not going well. But then I also wanted to come and say hello to Gunther and talk to some of you to discuss potential collaborations, partnerships, where there could be some new opportunities, I think, moving forward in terms of your new strategy, the new strategy that we just published last year as well. Can you hear me okay? I get a bit of echo, but that's just perhaps mine. Okay. So I've been at Q for 4 years now, almost. Time flies with the COVID pandemic. I still maintain an affiliation in Gothenburg, so I'm an active researcher, but I have the great honor of working with my wonderful colleagues at Q. I want to talk a little bit about Q, but before I want to talk about my own research and the things I've been doing in the past. And then when I arrived to Q, how many of you have been to Q here? Quite many, but half of you, perhaps not everyone. So I just want to say a few words. I don't want to make advertisement for Q. I just want to talk a little bit about our journal as an organization, and then I want to talk a little bit about my personal journey in terms of how I've decided to shift my own area of research more towards plant conservation and using some new technologies, including AI. So just to start off, the Neotropics is something that many of you I know have been working extensively in the American tropics, and it's this wonderful part of our planet. It's an amazingly diverse region in terms of both the landscapes with the Amazon rainforests, the Andes, but many different habitats, and of course the different species in those different ecosystems. And it's here that we have a profusion of water and many different life forms, of course, within those forests. And that's something that has attracted my attention, and I know many of you are sitting here today for a very long time. And the kind of thing that really struck me when I started doing my PhD in 2003 was this question that if you look at the work that Peter Raven and several of you sitting here perhaps today participated, yes, in that paper, thank you. So I read that paper in Science and looking at the distribution of plant diversity and the fact that in the African tropics we have something around 56,000 species, in tropical Australasia about 50,000, and then in the American tropics we may have more than those two regions combined. So a lot of my early questions in science have been around why do we have these patterns, and also how come some regions have become much more rich in species than others, and what does it mean in terms of conservation as well. So one thing I've been very keen on is to understand what's the relation between the past, the evolutionary history of clades, but also the geological history of the continent. How does that relate to current patterns of diversity? So already about 12 years ago, we published a synthesis for the northern part of South America, looking at how the landscape changed from just after the demise of dinosaurs, about 6 million years ago, where we didn't have any of the Andes, we didn't have the Amazonian River. We had a very different landscape, but gradually this completely changed, and we got the formation of the Andes, the formation of big wetlands in the western part of the Amazon, and then finally a lot of deposition from the Andean mountains into the western part of the Amazon. And this is, of course, a region which nowadays is extremely nutrient-rich. We look at the soil types. That's the highest diversity of different soil types. There are a couple of kilometers of sediments in these regions, and it's also where we have the highest tree diversity. that's been documented. So I think, of course, it's a correlational, it's not proof of the causation, but I think just trying to understand what are the elements which can perhaps explain some of the patterns we see today is something that has attracted my attention for a long time. And when it comes to the formation of mountains and the relation between mountains and biodiversity, several people here have been working a lot on this as well. We've been trying to do some global synthesis of our knowledge in terms of when did different mountain species originate, when did they go extinct, and also trying to identify phases. I'm sorry about the formatting here, I think it's a Mac PC issue, but optimal stages for biodiversity, and for instance, identifying that especially when you have a lot of change in the landscape, that's when you have a high degree of speciation and accumulation of species. So basically, if you look at from A here, so from left to right, it's just a schematic figure showing how you didn't have any mountains in the beginning, and then have some process like volcanism generating mountains, but then over time, those mountains will start to erode until they finally disappear or there's no geologic activity taking place. And it's within those two phases here in the middle that we have the highest accumulation of species. And of course, this is, again, still a correlation. We can't prove, but it seems that it's something that we see across many different mountain regions around the world. So we've been trying to go from the causational elements to more, from the correlation to more causation elements. I think Laura sitting here today has done some really great work in terms of identifying the relation between speciation and uplift of land, so the formation of mountains. We did some work for orchids, for instance, a few years ago, where we basically constructed phylogeny, so tree relationship, species trees of different species of orchids in a big clade of orchids, and we have here the coding of colors that represent the same ones on the map and on the phylogeny. What we can do here is to look at how surface uplift in this region is a model. It's very dependent on the mountain uplift. So a model where speciation rates are a factor of the surface uplift is much more supported than a model where it's not. So it's basically some sort of strong link between the formation of species and the uplift of surfaces here in the Northern Andes. And we can also use that information to track it back into the phylogeny. So we can basically create a heat map for speciation rates, and that allows us to really look at how is the speciation taking place across space and identifying some hotspots of speciation on the map. So at least for the Neotropical orchids, we have seen that the surface uplift seems to be increasing speciation, whereas with climate change, and especially the global cooling that occurred over this period of time, we had the opposite situation where this actually increased extinction. So speciation and extinction are the two main things that affect the number of species in a system, right? And these are two variables that are affected differently by both climate change and geological changes. So that's just one example. So I want to walk you through three examples of research areas in which I've been exploring, the formation of species in the Neotropics. My second one is about understanding the higher organization of life of species and how they interact with one another in forming biogeographic regions or bioregions. And that traces back really to Wallace, I think, and perhaps even earlier, in terms of identifying the main regions of diversity and how, for instance, you won't get any marsupials or any kangaroos outside, Australia. And that's really something that has struck naturalists for a very long time. But in a sense, it's been very expert-driven rather than informed by data. So what we've been trying to do is to develop methods, especially based on network clustering, to identify what are the major clusters of species on a spatial level, and using the network theory that really links species with one another depending on where they are. So how many people here are on Facebook? Yes, so Monica, we are friends on Facebook, but we are not friends on Facebook, but maybe you are friends with Monica, and we are friends through her. Maybe not, maybe Laura. But this is exactly the same situation with species. So sometimes species, they don't co-occur on the same place, but they have a third species which links them, and that carries biogeographic information, right? So that's what we're capturing from those network-based approaches. And this is just an example in Africa here, but we've been doing that for the Neotropics, where we basically use the current distribution of species and map it back on a landmass, and are able to then identify those major clusters of biogeographic regions. So we've done a series of papers in the Neotropics, but also globally, to identify those major clusters. And now we are just adding some more features to this software that we developed in InfoMap bioregions, where we're using the molecular phylogenies to inform on the timing. And also we can look at the biogeographic regions themselves, because there's a lot of discussion about, there's a lot of theory about evolution of species, how they form, they go extinct. But when it comes to ecosystems or biogeographic regions, there's of course much less understanding, right? So how old are the different ecosystems, and how isolated have they been from others, for instance? So if you look at places like Madagascar on this global map, which is this one here, and so that's just a plot showing how connected or isolated the biogeographic region has been in relation to others. You see a very high degree of isolation, which makes perfect sense because it's been isolated for more than 100 million years. And then other regions, such as in the Neotropics, in the Amazon, there's been more biotic interchange with other regions as well. And that brings me to my third example of things I've been doing in the past, which is to try and understand in more detail the assembly of those different biotas across space. And it is, in this case here, again, in the Neotropics. And what we've done was to synthesize lots of different molecular phylogenies for different groups of species, including plants, so ferns and flowering plants, but also looking at some different animal groups, because I'm very interested in biogeography, which is about comparing different taxa. And in this case here, what we did was to gather, as I said, lots of different phylogenies, and then to codify every single species by where they occur. So we've created software to do that. And then we can, based on the species occurrence, codify their occurrence, so presence or absence in different biomes. And then we can do biogeographic analysis to infer where species came from and where did they go. And in this case here, we've, for instance, identified that each one of those bubbles, I know it's a bit of a busy plot, but each one of those bubbles represents one major biome in the Neotropics, and the arrows represent dispersals, so species going from one to another. It could be either jumping or it could be range expansions. And what we can see here, the first thing is that there are lots of arrows, and those arrows mean that there's been substantial interchange. So basically, biomes feeding species into one another, right? And the other thing that you can see is that the one in the middle there, the Amazonian, is really where most diversity, most arrows came from. So basically, the Amazon was here the main source of lineages to other parts of the Neotropics. And also it was a main sink, so lots of species going back to the Amazon, but that's something that really shows something that perhaps most people already knew, that the Amazon is a major hotspot of diversity, but also in this case we could show that it actually fed species into many different parts of the Neotropics, really at the heart. And we can also look at this over time. So, was it something that happened the last few million years in connection with the glaciations, or has it taken place over a long period of time? And this just shows how dispersals took place between the Amazon and other biomes for 4 different other biomes here. And what we can see over time here from 60 million years up to now, there has been a very substantial exchange for tens of millions of years. So it's really a complex picture showing that the reason why we have so many species in the American tropics is partly due to the fact that those regions were exchanging lineages all the time. So, if you're lineaging in the Amazon and it gets up to the Andes or to the West Indies, you then diversify and create new species. But the reason why this can happen is that you had to have the lineage from the first place. So that really allowed us to understand a bit more about the formation of this very rich diversity in the American tropics. So, sorry, a bit thirsty. it was a bit about the research I've done so far, and that's the kind of thing that really got me out of bed every morning, I think. Just thinking about those big questions, why are there so many species here? How come? And I think it's really close to my heart to thinking biogeography and evolution because I'm really passionate about this. But then I came to Kew, and Kew is an interesting organization because it's been around for a long time, about 263 years, I think. And it's been very much about describing species, about describing diversity, but we also, on an institutional journey as well, and I'll come back to that. So at Kew, which I joined in 2019, as many of you have been there, it's a World Heritage Site, according to UNESCO. We've got now about 1,100 staff, 350 in science. So it's both technical staff, scientists, and others within the directorate. About 50 of them in Madagascar. It's much smaller than your program. You have about 150, 200 people there. But we are doing partnerships in more than 100 countries. And we don't quite know how many specimens we have because we haven't counted them, which is a bit embarrassing. But we are in the process now of digitizing our specimens. So we think we may have something around 7 million in the herbarium, but we don't quite know yet. As a side note, I was talking in Gothenburg, we thought we had 1.6 million, and then we counted, we had just 1 million, So let's see where we end up on. But that's Kew, and, apologies for just repeating things that many people here already know. But in terms of how we look like, for those of you who have not been there, so please do come and visit. But we have the herbarium, we have the Jodrell where we do the molecular work. In the past, if you were there more than 10 years ago, 7 years ago, perhaps it was almost like two different organizations, institutions, but it's really well integrated now with one another within Kew Science, thanks to the work that Kathy Willis, my predecessor, did in a new structure in 2014. And then, perhaps not many of you, how many of you have been to Wakehurst? Just a few of you. So most people who have been to Kew have not been to Wakehurst. We call it sometimes the Kew's White Botanic Garden in the south of London. It's about one and a half hours, I think, from Kew Gardens. But that's where we have the Millennium Seed Bank. And that's where we have, so it's 2.4 billion seeds from 40,000 species. And that's also where we coordinate the Millennium Seed Bank partnership. And I know many US organizations are part of the partnership as well. So seed banking has been a very important thing for us over the last decades, really. And then our wonderful staff in Madagascar as well. So just last year, we published then our 10-year corporate strategy. So what we're trying to do. And for an organization like Kew, very traditional and old-fashioned, to have a manifesto in the title of the strategy was quite radical. Interesting to get feedback from politicians as well. But we really think of this as a manifesto that we really want to see, how can we contribute to some of the biggest challenges we're facing today. And in parallel with that, we developed also a science strategy, which is focused on 5 priorities. I don't have to go through them here. I do have a couple of copies, but it's basically, quite similar to what many organizations, I think, including Missouri and others, we're trying to do about documenting plant diversity and so forth. But also these helped shape my own thinking about my own personal contribution in science and how I could actually try to contribute more to this agenda of conservation, of protecting. Also, I didn't mention the mission here, which is a single mission about understanding and protecting plants and fungi. I think it was very, very hard to get to this point, something that is very simple and people can actually remember, because otherwise it's just a bit, too many words. But that's the kind of mission we all trying to achieve. And of course, a lot of people in organizations are doing a very similar thing, but that's something that unifies all of us there. So since I joined Kew, then I was rethinking a little bit about what kind of things can I do to help contribute to that mission. And then I want to show again 3 examples. 3 is the magic number, I guess. So I'll give you 3 examples of the kind of work I've been doing in relation to that. And in a sense, I'm trying to understand, how did we go from here? I don't quite know whether this was how it looked like in Ecuador. I think it was in Ecuador, the heart of the Andes in 1859. Just a situation which is much worse than this. This picture is actually from Borneo, but we know it looks like the same in many parts of Latin America and so forth. And change in landscape use, so agriculture is the main driver of biodiversity loss. on land. And of course, we really have to understand what's driving this and what can we do. So really asking the question about where are we heading and what can we do to try and stop that. So I've been curious about the presence of humans in Latin America and the sustainable or not sustainable use of diversity. It's really hard because there's so little documentation there, but there have been some studies suggesting, human presence across most parts of the world, including Latin America, at a very low density for a very long period of time. So that's from 10,000 years ago up to now. But then, of course, something really happened here around the Great Acceleration after the Second World War, and then a drastic change in the human use of land in nature across the Neotropics. And if we look at, we did some analysis, this case here based on mammals actually in fossils, how diversity changed when humans arrived to different land masses. And that's a very consistent picture across all land masses almost, where you have the human arrival at some point, and then the extinction rates in red here, which really went up to the ceiling, and then the actual diversity here in gray, which declined across those three main land masses in the Neotropics. But we see the similar picture if you look at other systems as well. So of course we know that humans have been messing around and really causing direct extinctions of many different groups. It's harder to know for plants. There are just 600 species that have, a bit more than 600 that have documented to be extinct, but I think the actual number must be much, much higher than that. And nowadays, so I was just looking at IUCN Rarest assessment, so the extinction threat of species. We do about a third of them at Kew. And the picture is also quite consistent across different orders, where we have somewhere around 40% of all plant species likely to be threatened with extinction. And that's also the global average, so about 2 in 5 plant species likely to be threatened unless something drastic happens. So the causes of that are very clear. It's not really something to contest. The orange ones, I'm not sure if it's very clear to see the colors here, but the orange ones are all associated with land use changes. Those are the pictures I showed before. But then, of course, the direct exploitation of species, of trees for furniture, for instance, is one of the perhaps key issues in some parts of the Neotropics. But then, lots of species, over 6,000 species, directly affected by agriculture. And it's interesting because agriculture, food production is really the main driver of biodiversity loss or threats to species, but also one of the major contributors to climate change. So about 37% of global carbon emissions come from food production. So I think there's some really good opportunities as well. If we do change the food systems, if we do work in some of those areas, we can get synergies for both climate and biodiversity, and also the livelihoods. I think there's some really good opportunities there. So that's the kind of things that have been going in my mind, and we've been trying to do some further work on. And also to try and understand, on the ground, what are the differences? Because for those of you who have experience in South America, this is just a map of the satellite images and how much forest has been lost over the last 20 years. And it's a massive amount, really, across the whole region, and that's primarily driven by commodity production, soybeans mostly in Cerrado and other parts of southern Amazon and so forth, and then some more shifting agriculture practices in Central America, Northern Andes, and so forth. So there's some different drivers. As I'm sure many of you know here, it's not like major, huge plantations as you see with soybean fields, for instance, in South America. It's more the small scale, small landowners change in how they're using the land, and how that's contributing to forest loss. So I think, in a sense, many of us are here are perhaps biodiversity scientists, taxonomists, but I think contributing our knowledge to understand of those patterns is very important. The second example I want to talk to you about, and that's because also you have a huge presence there, you're much bigger than we are at Kew, but it's about Madagascar's biodiversity. And so how many of you have been to Madagascar? A lot, yeah, many of you. And I've just been there once, I have to admit, and it was interesting because I've done a lot of work in Latin America, I've done some work in Africa, but Madagascar to me was this very, very strange place, very special, fantastic people, but but also on the one hand, seeing this incredible diversity in the forest that we visited. But then on the other hand, the devastating effects of, poverty and the challenge that people face there, and the fact that you have to drive 10, 12 hours across a very bare landscape until you arrive to those small fragments of natural ecosystems. So I think that dichotomy is something that, at least for me, was very unique to see. I really got motivated to work with our colleagues. So basically with your staff, I don't know whether some of you were involved in this research that I'm looking at here, but we had 2 papers coming out last week or so, where we tried to synthesize the information we have about biodiversity levels across Madagascar. So on the one hand, we did an evaluation of the evolutionary history of lots of different plants and animals, and then we also looked at the conservation threats and opportunities for conservation in Madagascar. So I'm very pleased to show it here, because it's really a co-product between Missouri, KU, and several other organizations. In fact, 50 other organizations, I think we had 85 authors in 50 organizations. So really looking at all current knowledge for Madagascar and making it in a digestible way. And I'm happy that it came out just before COP15 as well, so we could have some of that data to discuss with policymakers in the negotiations. So basically this black line here shows species that are threatened below it, so that's all the reddish colors, and then species that are not likely to be threatened above it. And what I want to point out as well is that we did for plants, we developed a new technique using neural networks to learn from the current data that were assessed to predict, so using AI to predict the extinction threat of species that have not been assessed yet. So it's not a replacement for red list assessments, but it's a way of accelerating and complementing those assessments, and also identifying those species that are most likely to be threatened or not threatened, because that, then we can have the taxonomists and experts looking at them more deeply. So in some cases here, for instance, for the rosids, we had added more than 1,200 species, and we're able to actually get very similar results in terms of the proportion of species that are threatened and not threatened. So it made a lot of sense. But then if you look at things like ferns here, if you just consider the species that have been assessed, and it takes about a day, many of you may have done red list assessments, but it takes, at least for us, about a day to do an assessment for someone who's experienced. So it's very time consuming. But if you look at the species that have been assessed, most ferns seem to be doing well, right? Most of them are green, but actually by adding those species through the AI technique, 270 more ferns, we found that actually it's a very similar pattern to the others, where about half of the species are likely to be threatened. And we also found in the study that 90% of all plant species in Madagascar have some sort of threat. Even if they're not threatened now, there's some threat that is potentially affecting them as well. So just trying to get those numbers, I think, was an interesting exercise. And the other thing that was interesting that we did in this joint collaboration was to look at how Madagascar may or may not be able to reach the 30 by 30 target. I know the US is not a signatory of the Convention on Biological Diversity and Nagoya Protocol, but still, worldwide, it's a very important commitment now that countries are likely to sign, or not in a few days in Montreal. And I think from a biological perspective, and E.O. Wilson and others have already made the point, we need half of the Earth to protect 80% of species, or we need at least 30% of the world well managed, protected to safeguard a big proportion of the world's species. But then the question is, how does that vary across different countries? And I think there's a lot of lack of nuance in some of those texts being discussed. And my experience being in those negotiations now in Montreal is that a lot of those people have no idea what they're talking about. They're really sorry to say, but bureaucrats or policymakers who really don't get it. So I think getting some of our science and our knowledge into those discussions, I think, is so essential. And they were desperate to get scientists there. So when they found out, oh, are you a scientist? And they came up with all kinds of questions. So it is important for us to be fit into those discussions, and I think it's really something we should be doing perhaps even more. And I know some of you are really engaged in that as well. But basically, for Madagascar, the conclusions of our paper is that with 10% protected, just above 10%, it would be really hard, if not impossible, to increase it to 30% by 2030. So we make the point that it's better to invest on making the existing network of protected areas more effective, and to work with the communities around protected areas as well, than just creating paper reserves that you cannot effectively manage. So I think there are differences there. And then I know you, for instance, you guys are working in Gabon and Colombia, and those countries have already so much natural resource. They should not go down to 30%, of course. So I think we need to understand that there is variation, and different countries may have different opportunities to meet those targets moving forward. So these are the recommendations. Some of you may have seen it, but basically where we discussed about the increasing the effectiveness, that we should also increase natural capital forests outside protected areas to decrease the pressure within protected areas, that monitoring, biodiversity monitoring, so the work of capacity building, which is so crucial. And I know Missouri has been a fantastic partner in this and really driving that in many of your programs, but also addressing the root cause of biodiversity loss. I was a bit struck and a bit afraid, actually, when I was at COP. Some old-fashioned conservationists really still thinking very much about fortress conservation, fence things off, don't let people in. We have to save Madagascar's biodiversity. So I think a lot of that has changed, and people are now really understanding that it's more complex. We need to really work with the communities, because they're going to be the stewards of land and biodiversity. So yeah. And then, of course, working on the evidence rather than just political decisions, because that has a knock-on effect as well on conservation. So my last example, I said I will give you 3, is about conservation using AI. So AI is something that I've been quite interested in, and we at Kia as well are playing around with different techniques. So this platform we published earlier today, this year, is called Conservation Error Prioritization through Artificial Intelligence. And they use a technique called reinforcement learning. And that's something that if you play video games, right, you have to maximize how many things you collect, how many coins you collect, or perhaps which path you take. And if you play many times a game, you're going to increase your score, right? So you just learn the trick. You learn how to behave, what to collect, where to go, and then you maximize the reward. And this is exactly what the financial system does. So that's very useful as well in those contexts. How do you maximize value for money or revenue? Return on what you invest. And in this case here, we want to maximize how many species are protected over time. So what we did was to create a simulated system, where there are a number of different variables. So basically, think of Madagascar, or think of a state in the US, for instance, and then you divide it into many small grid cells, and each one of those you have different number of species, you have a different number of individuals, you have economic value, phylogenetic diversity, disturbance here in red, climate change, and so forth. So a biological system, and then you let it evolve, and the decision that needs to be made here is where to put a protected area. Where do you protect land in order to increase the biodiversity outcome? And then you learn under a fixed budget, which is always the case in conservation, how do you make the best decisions to increase the effectiveness of your protected areas. So this is basically something that seems to work really, really well. So we've done a lot of work demonstrating that. And it's something that I think the animation is working here. So basically, it's actually a quite difficult mathematical problem, because if you protect an area, the next one to protect is not necessarily the one that has more species, because you need to think of the complementarity of species that have already been protected. So again, under fixed budget, it's something that seems to, that outperforms any other method that we know is available. So for instance, in Madagascar, with this Captain framework, it not only gives a much higher proportion of species that are protected, but also a higher resolution of where, which areas should be protected or managed for maximizing the conservation. So that's something we're very keen on applying on more systems as well. So one question here is about data, because you really need data, and AI is quite data hungry. So I think there's some really exciting opportunities when it comes to the use of environmental DNA. I think at COP15, several groups were talking about this as well. So gathering data where you can measure, plant diversity, animals, in order through standardized ways without being an expert. Citizen science and mobile apps, iNaturalist and several other, that's exactly the kind of data you need for a system like this to work. And also at Q, we're doing quite a lot of remote sensing work where we can fly multispectrum LiDAR drones, so basically identifying single species in the landscape, and then you can calibrate that. And that's, I think, moving forward in the next few years is going to just increase more and more. So we can use remote sense data in combination with ground surveys to get the exactly kind of knowledge level we need to prioritize areas for conservation. So one thing we've been doing, and I know you work a lot on key biodiversity areas, we have a program called Tropical Important Plant Areas. And again, that's about putting plants on the map of conservation. I was a bit scared to see that almost everything talked about COP15 was about big mammals and birds. And there, for instance, 8 times more birds identifying KBAs, key biodiversity areas, than plants, for instance. Despite the fact that we only eat 9 birds, I think, and we eat more than 7,000 plants. But anyway, we need to bring plants into conservation. And this is a program we've identified now over 170 different areas in 7 countries, working with governments and local NGOs to really identify what their priorities are based on the best available data, but also managerial considerations. And the other thing that I've been talking about quite a lot is restoration, and we're not really experts in restoration, but we got together with a group last year and published just a series of very simple guidelines for successful restoration. I think you guys have a huge potential in this, Gunter yourself and several others. I think you could do revolutionary work in terms of telling the world about how not to do things and how to do things. So the right tree in the right place, right ways, and thinking about a more holistic approach about bringing benefits to biodiversity, to climate, and the livelihoods there. And that's also something we actually adapt in that AI framework to identify what are the key areas for restoration, and then that could be leading to a more successful reforestation program, and that's perhaps an area that we can be joining forces a bit. And the other thing that I've been playing around with is the idea of having some sort of early warning system. And I must say, I was in California with my family a few years ago, and we were just driving there in Death Valley, and then in that region, and then I got this text message out of nowhere, and then saying that flash flooding, seek refuge. I didn't know what flash flooding was, in Brazil. What is that? So, okay, we just drove to another place, and then in 15 minutes, there was this torrential rain coming. And that was fantastic, we got saved almost. And I had our 3 kids in the car, so it was really nice to have that kind of service. And in a sense, I think we do have the technology to develop something like this for species as well. So, if you do know like the distribution of a species based on herbarium specimens and digitized information from collections, and then all of a sudden you have a massive deforestation in the southern Amazon, or a major fire in Australia, as we've seen, combining the remote sense data with the kind of methodology I've been talking about, identifying red list species, those that are threatened, and area prioritization, this is actually able to identify that a species goes from being in one category to another in almost real time. In a sense, it would actually be possible to send someone there to collect seeds, because that's the last chance we have before the species, is critically endangered. But that would require quite a bit of efforts. At the COP15 meeting, there was a lot of talks about monitoring and evaluation. That's going to be a massive effort, I think, worldwide, to really monitor how biodiversity is changing over time, and whether we're actually going to meet the targets by 2030. So that's it. I just want to give you some conclusions and outlook. I think the biodiversity science, from my own experience, is both exciting and can be very useful as well. So I'm still passionate about evolutionary history and biogeography, but I also like to think that some of that knowledge hopefully can be useful to someone somewhere. And I think we can all reflect on our own personal and organizational ability to influence policy and to contribute. the world is in crisis. You know, I don't think we exaggerate to say that, and many of you who have been doing field work for decades in different countries, you know, we see every time we go back how bad things can look like, and I think how can we help is an important question to ask. And I think to achieve impact, I really hope we can join forces a bit more, and that's really why I'm here now. And with that said, I'll just make some shameless advertisement for my new book. And my first and perhaps last, because it was a pain to write it, but it was fun. The Hidden Universe. And I want to leave you with a picture of a piece of rainforest in the southeastern part of Brazil that my wife and I bought last Christmas. We had £200 in our account after that, but we put everything we had into buying rainforest, and we are now keen to establish this as a research and conservation station. So anyone interested in Brazil, I know traditionally people have not been working in Brazil, but everyone here is more than welcome to come and visit. It's directly connected to a very nice state park, so it's a beautiful area. Lots of new discoveries, I think, are waiting for us to come in and find them. Thanks so much.